On page 136 of your note packets, we're starting on lesson 6.2, dot product of vectors. So dot product is defined as the product or inner product of vector u and v. And the dot product is u dot v, which equals u1 times v1 plus u2 times v2. All right, so notice the dot product has two vectors for its input, and its output will be a scalar or a number, a constant. Okay, so there are some properties of dot product that we can look at. The first property is that u dot v is the same as v dot u, and this works similar to the commutative property of multiplication. If we had switched v dot u, it would be v1 times u1 plus v2 times u2, so it would be the exact same value. And then if we have u dot u, that's the same as if we take the magnitude of u squared. The third property is if we have 0, or the 0 vector, times another vector, we will end up with 0 the scalar. All right, property 4 actually has two parts. If we have u dot v plus w, so we have a vector and the dot product with the sum of two other vectors. That's the same as if we take u dot v plus u dot w, and that works both ways if we have the sum of the vectors first. So u plus v dot w is also equivalent to u dot w plus v dot w. This might remind you of the distributive property of multiplication. However, recall that these are vectors, and then what you end up with on this side are scalars. All right, and the fifth and final property that we're going to talk about is that if you have a constant times a vector, and you use dot product with another vector, that's the same as if you have a vector and the dot product with the same constant times the other vector. So it doesn't matter which vector you apply the scalar factor to, whichever one you multiply by that constant, you'll have the same answer, and that's the same as if you multiply the scalar or the multiplier and do the dot product first. So it doesn't matter which order you multiply that constant. All right, let's go ahead and take a look at actually computing the dot product. So we have two vectors here, and it looks kind of like the multiplication symbol, but this is specifically the dot product. So the dot product of these two vectors, recall, is the product of the first component, 3 times 5, plus the product of the second components, 4 times 2. So that equals 15 plus 8, which is 23. Notice our solution is a number, it's a scalar. Okay, for the next two parts of this example, you will need to recall something from the previous section. So note that the vector I is the vector 1, 0. Okay, this is a unit vector that goes only one in the horizontal direction. So the vector that looks like this with a magnitude of 1. So the magnitude of I is always 1. And then similarly, the j vector is our unit vector that moves vertically. So it moves vertically 1 unit, and the magnitude of j is also always 1. So these are two vectors that we use commonly when we're looking at only horizontal and vertical components of the vectors. Okay, as you can see, you'll do these two examples on your own, but you'll need to know the definitions of the vectors I and j for this last part of example 1. For example 2, we want to use the dot product to find the length of the vector u, which is 4, negative 3. Recall from the properties on the previous page that property 2 said that if I take the dot product of a vector in itself, it gives us the magnitude squared. So using that, if I take u dot u, it would give me the magnitude of u squared. So if I want just the magnitude of u, then I can take the square root of the magnitude squared, which means that I'm taking the square root of u dot u. So this was the property that we're using, and this is how we're going to apply it to find the magnitude of the vector. So now I'm saying, okay, the square root of 4, negative 3 dot 4, negative 3, which gives us the square root of the product of our first components, so 4 squared, plus the product of our second components, which is negative 3 squared. So this gives us the square root of 16 plus 9, which is the square root of 25, which is 5. Now remember, this is a magnitude, so we only want the positive square root of 25. All right, if you notice, this equation here is very similar to the equation that we used for the magnitude in the previous section. All right, so let's look at if there's an angle between two vectors. So if theta is the angle between the non-zero vectors u and v, non-zero meaning that there is an x and or y component. It's not the vector 0, 0. So we have non-zero vectors u and v. Then we have the cosine of theta equals u dot v divided by the magnitude of u times the magnitude of v. And we can use this same equation solved for theta to say theta equals cosine inverse of u dot v divided by the magnitude of u times the magnitude of v. Or we can use this equation and solve for u dot v and say that u dot v, so and u dot v equals the magnitude of u times the magnitude of v times cosine of theta. So we get all three of these equations that are really saying the same thing, but they're solved for different parts of the equation. All right, on the next page, we're talking about orthogonal vectors, and those are vectors u and v, and they are orthogonal if and only if their dot product is 0. So u dot v equals 0. Let's apply this to example 4. We want to prove that the vectors u, 2, 3, and v, negative 6, 4, are orthogonal. So in order to prove that they're orthogonal, we want to prove this by showing that their dot product is 0. So we're looking at u dot v, or 2, 3 dot negative 6, 4. Dot product, again, is the product of the first components, 2 times negative 6, plus the product of the second components, 3 times 4. So the product of the first components is negative 12, plus the product of the second components is 12. Negative 12 plus 12 equals 0. So we know that they are, in fact, orthogonal. All right, next let's take a look at projections. So the projection of the vector u onto the vector v is if u and v are non-zero vectors, then the projection of u onto v can be represented by this diagram. If we have here vector v, and here we have vector u, and they have a common point, the initial point in common, then we draw a line kind of perpendicular to vector v, and this new vector is the projection of u onto v. So it's a projection of u, and it's kind of like a shadow. So if we had a light shining from above u, its shadow would be the projection of u onto v. And we can calculate this projection onto v of u is equal to u dot v divided by the magnitude of v squared multiplied to v. Okay, so here we have u dot v is a scalar, the magnitude of v squared is a scalar, and then we multiply it to v, which is a vector. So a scalar times a vector results in a vector. So we know that the projection of u onto v is a vector. So this is a vector. This part is a scalar. V is a vector. And if you have a scalar times a vector equals a vector. All right. So let's see if we can use this in example 5. We want to find the vector projection of u onto v and then write u as the sum of two orthogonal vectors, one of which is the projection onto v of u. Okay, so first we want to realize that our end goal is to write u as the sum of two vectors. So let's call them u1 plus u2. Okay, so this is a reminder that u is going to be written as a sum of two vectors. Okay, if one of our vectors is going to be the projection, so let's say that this is equal to the projection onto v of u plus whatever our second vector is, right? In order to find out the value of that second vector, we already know u, we know how to calculate the projection, so we can say that if I subtract the projection from both sides, I'll be able to find the second vector equals u minus the projection onto v of u. Okay, so now let's calculate the projection so that we can calculate our second vector. So the projection of u onto v equals u dot v divided by the magnitude of v squared times v. So we have 6, 2 dot 5, negative 5 divided by the magnitude of v squared, which we could calculate as v dot v. So we can do this as 5, negative 5 dot 5, negative 5. And then we're multiplying that whole thing by the vector 5, negative 5. All right. So dot product, I take 6 times 5 plus 2 times negative 5 divided by 5 times 5 plus negative 5 times negative 5, and then I multiply that to our vector v. All right, so 6 times 5 is 30 minus 10 divided by 25 plus 25 times 5 comma negative 5. So simplifying this further, we have 20 divided by 50 times our vector. This fraction can still be simplified to 2/5 times our vector v. All right, now notice I could still simplify when I distribute the 2/5 to my vector. I'll be able to simplify by 5. So this is 2 times 5 over 5, comma, 2 times negative 5 over 5, which actually simplifies to 2 comma negative 2. So the projection of u onto v is the vector 2 comma negative 2. And this is what we're calling our u1. So in order to calculate u2 equals u minus our projection. So we start with 6 comma 2 minus 2 comma negative 2. When we subtract two vectors, we subtract their components. So 6 minus 2 comma 2 minus negative 2, which equals 4 comma 4. So our final answer, u equals 2 comma negative 2 plus 4 comma 4. Where the first vector here is our projection. All right, on the next page, looking at example 6, we want to determine whether the vectors u and v are parallel, orthogonal, or neither. Now remember, if they're parallel, then they'll be pointed in the same direction, which means that they can be scalar multiples of each other. So here, if I'm looking at u is 5/3 and v is negative 10/4, comma negative 3/2, it looks like I might be able to simplify v to have a factor of 5 comma 3. So let's try that first. Let's start by simplifying 10/4. So v could be rewritten as negative 5/2, comma negative 3/2. Now I see a common factor of negative 1/2. So we can factor that out. Negative 1/2 times the vector 5 comma 3. Now see how this is actually equal to negative 1/2 times u. That means that these must be parallel. All right. So using this tactic of finding parallel vectors, and then the previous method where we found orthogonal vectors by using the dot product, and if neither of those methods work, then it is neither. Go ahead and try the other two examples, or the other two problems in this example. Now on example 7, we're using what we know about vectors to solve kind of a physics problem. So Juan is sitting on a sled on the side of a hill inclined at 45 degrees. So it looks something like this. We have a hill inclined at 45 degrees. So this is 45 degrees. And we have Juan sitting on a sled. Excuse my drawing. Okay. The combined weight of Juan and the sled is 140 pounds. So now weight it is dependent on the gravitational pull, so it has a force that's going straight down. So this is 140 pounds, and it's going down, so it's negative 140 pounds. Okay? What force is required for Rafaela to keep the sled from sliding down the hill? So now we have another character here, Rafaela, holding the sled, and we want to know what force does she have to exert to keep the sled from sliding down the hill. Okay, so what we're really looking for is this other force. All right, so we're looking for this force here. Okay, so let's start with what we know. We know that the force from gravity is 140 pounds downward. So that's negative 140 only in the vertical direction. So we can call that negative 140J, or we can call that 0, negative 140, right? Those two things mean the same thing. They represent the same vector. Okay, we also know that the vector of this hill, right, this hill is on a 45-degree angle. So if I wanted to find, for example, the unit vector of this hill, we can say the hill has a vector of cosine of 45 degrees, comma, sine of 45 degrees, right? This is from when we were talking about unit vectors. And from the unit circle, we know that the values for these are the square root of 2 over 2, comma, square root of 2 over 2. And that matches what our hill looks like, right? At a 45-degree angle, our unit vector should have those values. Okay? Now what we want to find out is what force is required in order for the sled not to be pushed down the hill. Okay? So the force required can be calculated by, and this is where you need some prior knowledge. So if U is a force vector, then the magnitude of the projection results in the force in that direction. So that tells us that, let me draw this kind of triangle a little bit bigger. I have a force vector here that is negative 140J, right? And I want to find out, this is the hill, I want to find out what projection onto that force vector is the force that I need. So if I'm taking this vector and projecting it onto the hill, that means it has to be at a right angle to the hill. So there's my right angle, okay? So this is the force that we're looking. That's the vector that we need to find. Just the projection. All right. We know that this is a 90-degree angle. We're looking for the projection of our force from gravity onto the hill. Okay. So let's call the force from gravity, let's call this F1. All right. And let's call the hill, we'll call it V. Okay, so this I've called F1, and we call this V. So we're looking for the projection of force onto the hill. And we'll calculate that by the projection onto V of F1. Okay, and from our equation, we know that that's F1 dot V divided by the magnitude of V squared times V. All right, now remember our V was a unit vector, so our magnitude is 1. So I know 0 times the square root of 2 divided by 2 is going to be 0. 0 plus negative 140 times the square root of 2 divided by 2 is going to be negative 70 times the square root of 2 times our vector square root of 2 over 2, comma, square root of 2 over 2. So our magnitude was 1, our dot product gave us a value of negative 70 times the square root of 2. And now we need to multiply the scalar and the vector. So we have negative 70 times 2 divided by 2, comma, negative 70 times 2 divided by 2. which gives us a reduced vector of -70, -70. Okay, but remember, the force is the magnitude of the projection. So if we're calling this F from our diagram, then we need the magnitude of F. And that equals the square root of -70 squared plus -70 quantity squared, which equals, now a negative squared plus the same value squared is the square root of 2 times 70 squared, which is 70 times the square root of 2. Using a calculator, this is approximately 99 pounds. So the force that needs to be applied in order to prevent the sled from sliding down the hill is 99 pounds. All right, we're almost there. So on page 140 of your notes packets, the last page of 6.2, we're looking at work. If F is a constant force whose direction is the same as the direction of vector AB, then the work done by vector F in moving an object from A to B is calculated by the equation W equals the magnitude of F times the magnitude of vector AB. Okay? For any vectors that are not pointing the same direction, so this would work if they are or if they aren't, for any vectors, F and AB, we could calculate work to be the magnitude of F times the magnitude of AB times cosine of theta. So the reason we can use this first equation, if they're pointing in the same direction, is because our theta would be 0. They're pointing in the same direction, so the angle between them is 0. So this would just be magnitude of F times the magnitude of AB times cosine of 0, which is 1. All right, so our first equation here is just a simplified version of the second equation. So let's see if we can use this. On example 7, find the work done by a 10-pound force acting in the direction 1, 2 in moving an object 3 feet from 0, 0 to 3, 0. Okay, so let's start off by saying that our magnitude of our force is 10, right? It's a 10-pound force. And it's in the direction of 1, 2. So let's find out what is the magnitude of 1, 2. And the way we can find that is the square root of 1 squared plus 2 squared, which is the square root of 1 plus 4. So this is the square root of 5. So to find F, we can say its magnitude times its unit vector. So 1, 2 divided by its magnitude, which is the square root of 5. Okay, so we know that our force vector is 10 divided by the square root of 5 times 1, 2. Okay, so here I need to find AB. Vector AB is from 3, 0 to 0, 0. So from 3, 0, 3, 0, 0, 0. So I get the vector 3, 0. Okay, so if I need to find the work, I know from the second page of our notes packet that this can also be calculated by F dot AB. So now I have F, I have AB, so F dot AB equals 10 divided by the square root of 5 times 1, 2 dot 3, 0. And I'm going to do the dot product first. So this equals 10 divided by the square root of 5 times 1 times 3 plus 2 times 0, which equals 30 divided by the square root of 5 Put that into a calculator and you will find that is 13.42 foot-pounds. And that is a measurement of work. All right. Take a few moments to reflect on this section and then write a summary of what you learned in the box below.